Cornell Rover has worked tirelessly over the last 7 months to design and manufacture a URC-ready rover. We're so excited to unveil this year's rover, Hyperion. Our team is broken into 6 different sub-teams organized by discipline. The arm sub-team is responsible for developing all aspects of the rover's robotic arm. The drive sub-team oversees development of the rover's suspension, wheels, frame, and electronic housing. The electrical sub-team is responsible for all electrical components, including the rover's communication systems and embedded firmware. The software sub-team operates rover controls and designs the autonomous system. The Astrotech sub-team is in charge of ensuring that the rover is able to complete competition science tasks by researching, developing, designing, and building all scientific hardware. And finally, the business sub-team is in charge of team finances, web and presentation design, and both public and sponsor outreach.
The academic year is split into 3 development periods: a fall design phase from August to November, a winter manufacturing phase from November to February, and a spring testing phase from February to May.
This year, the ARM sub-team has made significant advancements, focusing on precision and dynamic control. Our 6 degree of freedom arm is manufactured from custom aluminum joints and carbon fiber tubing. We have integrated strain wave gearboxes at each joint, significantly reducing backlash while maintaining a lightweight, high gear ratio. This choice enhances the arm's payload capacity while supporting highly accurate control. Absolute magnetic encoders are fitted on each actuator, allowing for absolute position control using inverse kinematics and additional control using a new dedicated miniature arm controller. A parallel end effector is mounted at the end of the arm with an integrated camera and laser to aid in manual operation for high precision tasks.
Based on the performance of our previous suspension, this year the drive sub-team implemented a damped rocker system, enhancing dynamic stability and reducing vibration. Our new wheel design features hub motors and pneumatic off-road tires, increasing efficiency and eliminating frictional losses of geared systems. The redesigned frame uses bent sheet metal for maximum space and modularity, integrating wire routing and connector panels for streamlined maintenance. Additionally, our electronics housing is fully detachable, simplifying servicing.
This year, we recreated our brushless drive methodology to use Modius R411 brushless motor drivers. We integrated these powerful drivers into our rover-wide CAN bus while developing a robust hardware abstraction layer to expose motor control functionality to our software team. Our team has designed custom PCBs for any external hardware that requires specialized electrical control. This includes brush motors, sensors, radio power, and more. Because our system supports a versatile set of hardware, an intelligently designed communication stack is a necessity. Our newly designed central communication system uses numerous layers of communication protocols, including CAN-FD and SPI layers. Additionally, the host software transmits commands through a serial connection. All of these layers have been carefully architected to maximize throughput, allowing for quick feedback and a responsive operating experience.
This year, the software sub-team has made significant advancements to our system.
Integrating a Z stereo camera with GPS and odometry sensors, we've enhanced our location estimation and object detection in autonomous tasks. Our autonomy now relies on behavior trees for competition scenarios and decision trees for efficient navigation and AR tag detection. A pivotal upgrade is the incorporation of the NVIDIA Jetson Orin Nano, boosting our processing power. This allows us to fully utilize the latest ROS packages, improving our capabilities in point cloud processing, inverse kinematics implementations, and object detection. We've also improved our node management framework, ensuring better fault handling and system reliability.
This year's science payload features spectroscopic, chemical, and sensor tests to identify potential signs of life in soil samples and geological features. To test the soil for extant life, we use a fluorescence spectrometer in combination with our chemical fluorophore that binds to amine groups and proteins and becomes highly fluorescent once bonded. We use a low concentration acid to detect extinct life, which we supplement with additional sensor data and camera feeds to draw conclusions regarding habitability and the presence of life in a given sample.
The Astrotech sub-team is focused on creating a life-detecting science array to analyze our samples on the rover. The soil collection system features a 4-bar linkage to raise and lower a scoop to each site. Each soil sample is then separated into different chambers. One part is sealed dry to deliver to judges, while another part is mixed with low-concentration acid, which would react with fossil carbonates if present. The rest of the soil is combined with a neutral solvent, filtered, and pumped into a cuvette for analysis in our onboard spectrometer.
With a focus on reliability, we have a rigorous testing plan. We've divided the entire team into 4 different task teams, one for each URC mission. Each task team lead develops and executes an incremental testing strategy, gradually bringing the rover up to full functionality. Towards the end of the semester, we put both the rover and the competition team through 2 mock competitions. Hyperion and the rest of the team are just about ready for competition, and we hope to see you in Utah.